Hi friends, now we are going to see fourth part of MATLAB Onramp course on reinforcement learning, RL. Let's start. In this video we are going to cover define agents, topic in RL Onramp course and subtopics as shown here. Okay. Then see here submodules covered in this video are given. Okay. An agent turned observations into actions. How do you represent that in this dice game? The observation is the current target, the action is the choice of die to roll. So theoretically, the agent's policy is just a function from target values to choices. In reinforcement learning, an agent that maps observations directly into actions like this is called reasonably enough, an actor. This seems like the obvious way to represent an agent, but surprisingly, it turns out that a different representation can work better. Remember that your actor will start with a random policy and try to improve it over many episodes. Improving means getting a higher total reward. And the dice game, the reward at each step is -1. No matter whether your choice of die was good or bad. But good choices will get you to the target in fewer steps, so the total reward will be higher. But given that one game involves many choices, how do you know which choices were good and which were bad? How do you update your policy to choose the better actions? You'll need to play a huge number of games before you can sort out how choosing die number 4, when the target was 7, affected the overall reward. Instead of an actor, you could use a critic. Critics don't directly choose an action, they just critique how good it is to be in a particular situation. For the dice game, the target can be 1 to 20, so there are 20 states, ignoring the final state when the target is 0 in the game ends. In each state there are 5 actions you could choose. A critic will try to figure out how good each of the 100 possible situations is, that is, how good is it to choose die number 4 when the target is 7? For the dice game, this measure of goodness, the value will be the expected total reward of that episode, that is, the negative of the average number of steps it takes to reach the target. How does the critic determine this value? Just like the actor, initially it has no idea, but it can start to estimate it by playing the game repeatedly. Each time the agent chooses die number 4 when the target is 7, it can look up the table and see what it thinks the total reward is going to be. Then it can play out the game and get an actual value, then use that to adjust its estimate. Note that your critic is just building this table of values, not telling you which die to choose. But it's easy to get a policy from the values. Observe the state and look up the appropriate row in the table, then choose the action that has the best value. However, remember that your critic is trying to figure out the right values by experimentation, so you need to explore. If you always choose die number 4 when the target is 7, how will you ever figure out the value for choosing die number 2 instead? So typically while learning, you'll mostly choose the action with the best value, but occasionally make a random choice instead. Your critic's measure of value is denoted by Q for quality, and so this table is called Q table. The process of refining your estimates for the Q values is called Q learning, one of the many training algorithms used in RL. Of course, the Q table for the dice game is very small. Real problems may have many more states and actions. There are other methods designed to handle that, which you'll see later. In the next activity, you'll create a Q-table representation of an agent for the dice game.
Task 1. A Q table has a row for each observable state and a column for each allowable action. You can use the RL table function to create a Q table for a Q learning RL agent. T equal to RL table of states comma actions, where states and actions are environment interfaces created with RL set spec. Okay, now task is use the RL table function to create a Q table called T for a dice game. The observable state are stored in the variable OBS info, and the action choices are stored in the variable called act info. Okay, the syntax is T equal to RL table of OBS info comma act info. Okay, Q values are stored in the table property of a Q table. Task is use dot notation to extract the table property of T to the matrix called Q vals. Okay, the syntax is Q vals equal to T dot table. Okay, task 3, before training Q values are all set to 0 by default. These values are updated during training. Our task is use the rand function to create a 21 by 5 matrix of random Q values stored in this matrix in a variable called rand Q valves. Okay, syntax is rand Q valves equal to rand of 21 comma 5. Okay, and output as shown in the output panel. Okay, Q values are typically determined during training. However, you can manually set them by directly modifying the table property of a Q table. Okay, task is use the dot notation to set the table property of T equal to matrix rand Q valves. Okay, syntax is T dot table equal to rand Q valves. Okay, and output as shown in the output panel. Okay, with the Q table T, you can create a critic for a Q learning agent. Of course, with randomly chosen Q values, the critic won't actually be any good. You can use the RL value function to make a Q value critic from a Q table. Q critic equal to RL Q value function of Q table comma states comma actions, where states and actions are environment interfaces created with RL finite set spec. Okay, our task is use RL Q value function to create a Q value critic called critic from the table T. Recall the observable states are stored in the variable OBS info. The action chooses are stored in the variable act info. Okay, our syntax is critic equal to RL Q value function of T comma OBS info comma act info. Okay, and output shown as in the output panel. Okay, task 6, now that you have your critic, you can use the RL agent function to create a Q learning agent from it. Agent equal to RL Q agent of Q value critic. Okay, task is use a RL Q agent function to create a Q learning agent called agent from critic. Okay, syntax is agent equal to RL Q agent of critic. Okay, output shown in the output panel. Okay, task 7, use the command n comma win equal to play dash of agent comma SLENV to simulate playing the dice game with the agent you just created. Okay, and the syntax is n comma win is equal to play dash of agent comma SLENV and output shown in the output panel. Okay, the meaning of Q table. Recall, a Q table shows the value of each pair of states and actions. In this activity, you will visualize a Q table for a trained agent for a dash game. Okay, you will also visualize how the Q table create to the agent's policy. Okay, visualize a Q table. In the task 1, the Q values are stored in the table property of the table representation. The first row of the Q table for the dash game corresponds to the terminal state target equal to 0. Our task is extract all but the first row of the table property of T. Store the result in the matrix qvals. Syntax is qvals equal to T dot table of 2 colon end comma colon. Okay, output has shown in the output panel. Okay, task 2, use the image sc function to visualize the values in the qvals. Use the color bar function to show the mapping of the values to colors. Okay, image sc of qvals then color bar. Okay, the output has shown in the output panel. Okay, the best action for each state is determined by the maximum value in each row of the Q table. You can use the optional dimension input to the max function to find the maximum value by row. The optional second output from the max function contains the column indices to the maximum elements. Okay, max comma x equal to max of x comma square brackets comma 2. Our task is find the maximum values of the rows of qvals and their corresponding function indices. Store the values in the variable called mxq and the indices in col. Okay, syntax is mxq comma col is equal to max of qvals comma square brackets comma 2. Okay, output shown in the output panel. Okay, now task 4, the column indices of the maximum q values represent the agent policy call of n. In the optimal action for state n, our task is use the hold on and hold off commands to add the plot to the image. Plot the column indices on the horizontal axis and the states 1:20 on the vertical axis. Use the black marks to make the data points. Okay, syntax is hold on then plot col comma 1:20 comma xk then hold off, and output is shown in the output panel as given here. Okay,
When you have a limited number of states and actions, you can represent a critic as a table of values, a Q table. But if you have many states in action, the table may be huge. And what if your observation is height, or position, or velocity? What if your action is a force to apply or a throttle setting? Now you have infinitely many Q values. so a table isn't a great way to represent them. The idea of a critic is still useful. You just have to represent it differently. The critic's value is just a function of the observations and actions, regardless of whether they are discrete or continuous. You can represent a continuous function in various ways. But the most common approach in RL is to use a deep neural network. A neural network is just a function, a recipe for turning inputs and outputs, that has many parameters that control the function shape. You can choose these parameters, known as the weights and biases, to make the network produce any output from any input. That means a neural network can learn to represent any function. When used as a critic, the network represents the value function. How does the critic learn to represent the value function? As with Q-learning, you start with no knowledge, then build better estimates by running experiments and comparing what you thought the value would be in a given situation with what it turned out to be. Then adjust the parameters of the network to shift your value function towards the actual value. With one observation and one action, you can visualize the value function as a surface. But in practice, you will have multidimensional observations and actions, so your value function will have many inputs although you can't visualize a 12-dimensional surface. You can create and train a neural network to represent it just the same. In the next activities, you'll create Q-learning agents that represent their critic with a neural network.
A network-based agent for the dash game. With only 20 states and 5 actions, the dash game can be well represented by a Q-table agent. However, with more states and actions, you might want to use a neural network instead of a table to represent your critic. Okay, as shown in figure, Q table agent is replaced by deep Q network agent. Okay, in this activity you make a deep Q network DQN agent for the dash game, even though in practice this is overkill for such a simple problem. Okay, task 1, you can create an agent by calling the appropriate RL star agent function, whereas the wildcard star is replaced by the agent type such as DQN with just the observations and action specifications as input. Okay, syntax is agent equal to RL DQN agent OBS info comma act info. This will create an agent using a predetermined default architecture for the neural networks that represent the agent's actor or critic. Our task is use the RLDQN agent function to create an agent called agent with the default network for the critic. Okay, then the syntax for task 1 is agent equal to RLDQN agent of OBS info comma act info. Okay, the output is shown in the output panel. Okay, retrieving the network from an agent. It is easy to create an agent and typically these default agents will work well. However, how do you know the architecture of these default networks? Can you modify them? Or how do you change any options or properties of these default actors and critics? You can use the get actor and get critic functions to get the actor and the critic from an agent. You can use the get model function to get the underlying neural network from an actor or critic. Okay. Task 2, the getCritic function takes an agent as input and returns its critic as output. Our task is use the getCritic function to extract the critic from agent and store it in an variable called critic. Okay, syntax is critic equal to get critic of agent. Okay, and output is shown in the output panel. Task 3, use the getModel function to extract the neural network from critic and store it in a variable called net. Syntax is net equal to getModel of critic. Okay, and output is shown in the output panel. Task 4, the variable net represent a neural network. You can see the structure of the layers in the neural network by plotting it. Syntax is plot of net. Okay, our task is use the plot function to visualize the layer structure of net. Okay, syntax is plot of net and output shown in the output panel. Okay, neural network layers. The default critic of a DQN agent is represented by a neural network with 6 layers. What is neural network and how do they work? What are the layers and what do they do? To answer these questions are: a deep neural network is made up of multiple layers. Each layer receives input from the previous layer, performs an operation on the input, and passes the output to the next layer. Okay. Then for actor or critic networks, typically the inner or hidden layers or fully connected layers or activation function layer. Okay, as shown in the figure. Okay, a fully connected layer consists of a number of neurons. Each neuron is a mathematical operation, multiply and the input by a constant called the weight and the another constant called Bayes. The resulting value is then passed to the next layer. Okay, in a fully connected layer, each neuron takes input from every neuron in the previous layer and passes the output to every neuron in the next layer. This measures that each neuron has many weights. Okay, in between fully connected layers, there are typically activation function layers that apply a function to introduce nonlinearity. Okay, as shown in the figure. Some commonly used activation functions are the rectified linear unit ReLU, which leaves positive input unchanged and set negative input to 0. Okay, the hyperbolic tangent with smoothly maps all inputs into the range -1 to 1. Okay, architecture for a q value network. The default critic for a DQN agent is represented by a neural network with 6 layers. Okay, the network is contained in a variable. One of the properties of the variable contains an array of the layers of the network. In this interaction you will examine these layers. Okay, let's see. Task 1. The variable default net contains the critic network from the default DQN agent. The layer properties of a network variable holds in an array of the network layers. You can use dot notation to access any property of a network variable. Layers equal to network dot layers. Now our task is use the dot notation to extract the layers property of the network default net. Store the result in a variable called layers. You may want to leave off the semicolon to see the result. Okay, our task syntax is layers equal to default dot layers. Output can shown in the output panel. Okay, the q value function, one input 5 outputs. In the dice game the agent observes a single value, the target, and chooses between 5 actions the dice. This determines the input and output layers for the critic network. It takes a single input, the observation, and produce 5 outputs representing the 5 q values for the combination of that observation and each die. Okay, then the fully connected hidden layers can be of any size. The default network uses two hidden layers of 256 neurons. Okay, task 2. The layers of the network are represented by a vector variable. Each element of the vector corresponds to a layer of the network. You can use standard array indexing to extract individual layers. Nth layer equal to layer of n. Okay, our task is extract the second layer of the default network into a variable called fc, and the syntax is fc equal to layer of 2. Okay, output is shown in the output panel. Okay, task 3. You can combine dot and array indexing to extract a specific layer from the layers property of the network. Nth layer equal to network dot layers of n. The variable trained net contain a critic network from the trained agent. It has the same structure as the untrained critic network default net. Okay, our task is extract the second layer of the pre-trained network trained net into a variable called fc trained. Okay, and syntax is fc trained equal to trained net dot layer 2. Okay, output is shown in the output panel. Okay, network parameters, weights and biases. A fully connected layer fc and fc trained appear identical. what is the difference between them? Recall that the weights and bases of fully connected neurons determines how they turn input into outputs. Okay, when the first created such as default net, a network has random weights and bases. When an agent is trained, the weights and bases of the network are updated so that the network turns inputs into outputs in a meaningful way. In this case, such that a given observation for the target value produces the correct q value for each choice of dash. Okay. Task 4. A fully connected layer has arrays of weights and bases that represent the parameter for each neuron. The value for these parameters are typically determined during training. Our task is use dot notation to extract the weights property of fc into variable called wd. Similarly, extract the weights property of fc trained into a variable called wt. Okay, our syntax is wd equal to fc dot weights, wd equal to fc trained dot weights. Okay, output is shown in the output panel. Further practice. The weights of hidden layers don't have any obvious meaning. The important feature of a critic network is the 5q values that the network produces for each input value, the observations corresponding to the target values. The local function visualize q passes each target value through the network and record the 5q values returned. It then visualizes the resulting q table as an image. Visualize q default net and visualize q trained net. Okay, because the weights and bases of default net are random, you will see the different q table each time you run the script. Okay, the syntax is visualize q default net, visualize q trained net, and output shown in the output panel. Okay, up to now we covered define agent subtopics, critics and q value, and representing critics with neural networks. In next video we will start actors and critics subtopic. Thank you very much.